Okay, let's start. Okay, so hello everybody. My name is Michela Ceria from Politecnico di Bari, and welcome to the lecture on foundations of multivariate crypto. We start by saying that solving a polynomial equation system in the problem is very important with different applications in different science fields. For example, you can see a list of them, but you can also add robotics to them. I mean, there are really a lot of them. And the standard tool in order to solve such a problem is given by Gröbner basis. Gröbner basis are a sort of rewriting of your system that makes it simpler to be solved. For a given system, you have not only one Gröbner basis, and some of them are more efficient to be found. There are also applications to crypto, and in particular to the so-called multivariate public key cryptography, in which you have crypto systems where the public key is a finite set of polynomials over a finite field. And in general, the general scheme is you have Alice who wants to send P to Bob, this message. So she evaluates the public key by Bob at this point. The public key, we said, is a finite set of polynomials, so you can evaluate it at a point, getting in this B1, BR. Well, Bob uses the secret key and can solve more efficiently the system and recover the message. Here you can see a list of some of the multivariate public key crypto systems that you may want to deepen study. Well, if you want to solve a system of polynomials that is multivariate, nonlinear, randomic, well, this is NPR. But we are not safe by saying that a system is secure since it relies on the resolution of a polynomial system, because in cryptography, Bob has got a specific trick in order to recover the message from the system. It can solve more efficiently the system. So the system cannot be really random. There is a structure inside the system, and the structure of the system can uncover the site to attacks. So when you create a crypto system or when you analyze a crypto system, you can't say directly, well, oh, okay, I have to solve a polynomial equation system so it is secure. No, you have to examine the structure of your system. Let's see some notation for this lecture. This P is the polynomial ring and K is my field. This is the order I always put on the variable. So smaller index means smaller variable. And I define with T the semigroup of terms. So the set containing all monomials. Well, on this you can define a term ordering that is an order on these monomials, that is a well order. It is a total order and it is multiplicative. What does it mean? It means that if you have an inequality of this kind and you multiply both sides by the same monomial, so for example, here I multiplied by x gamma, the inequality is preserved. When you have it, for each polynomial, you can define the leading term. That means the maximal term inside the polynomial with respect to the ordering, the leading coefficient, that is its coefficient, and the leading monomial, that is their product. Finally, you can take the polynomial and subtract this leading monomial, getting the other monomials with their coefficients. This is what we call the tail of a polynomial. We define then a couple of subsets of T with special properties. J is a subset of T and it is a semigroup ideal if it is closed under multiplications by elements of T. So if T is an element in J and I take a monomial S in T, ST is an element of J as well. And a set N is an order ideal if it is closed under division. So if I have T in N, then all divisors of T are in S as well. For each set of polynomials, you can define T of F, that is the set of all leading terms of the elements in F, your set of polynomials. Then you can define the semigroup ideal generated by this set and the complementary set that is actually an order ideal. And with all this definition, we are ready to give the core definition of Gröbner basis. Let's take an ideal of the polynomial ring, and G is a subset of this polynomial ring, of this polynomial ideal. Well, G is a Gröbner basis with respect to your term ordering if the semigroup ideal, so this one the semigroup ideal given by the generated by the leading terms of the elements of G is actually equal to the set of all the leading terms of the elements in the ideal. The first algorithm in order to compute Grobner basis that actually is classical, important for an historical point of view, and from my point of view, also for a pedagogical point of view, is the classical Buchberger algorithm. This algorithm, you take a generating set of polynomials, here indicated then by isolating which is the leading term and which is the tail. And you take them, these generators, in pairs. Using these pairs, you compute a new polynomial, this one, that is called S polynomial, in which you put these two polynomials together and you eliminate the leading terms by a sort of gain with least common multiples. Here you see an example. Then you have to make reduction. So every time you see a multiple of the leading term of a generator, you substitute the occurrence of this leading term of the generator by minus the tail. And you can do that monomial by monomial by monomial until you have nothing more that can be reduced. So nothing more that is multiple of the leading term of a generator. If you get something that is non-zero, then you take this polynomial that you got, insert it in the generating set and use it again in order to compute other S polynomials and make other reductions. And you do that as soon as everything goes to zero. In this way, you get your Grobner basis. This algorithm has historical and pedagogical importance, but it's actually not used in practice because it's actually not efficient, reducing as a cost. So, for example, you want to reduce only when it's really useful. There are criteria in order to establish whether an S polynomial is useful or not. Criteria by Buchberger himself, criteria by Gebauer and Müller. So you have criteria to understand whether an S polynomial is really useful or you can drop it. But there are also more efficient approaches. In particular, you have involutive divisions and bases. These involutive bases are actually special kinds of Grobner bases, especially used in physics because they have a strong link with the partial differential equations, and algorithms like F4 and F5 by Fougère that use linear algebra in order to get bases. Moreover, well, there are a lot of problems that classically have been solved by saying, well, if you have got a Grobner basis of your ideal, you have the solution of your problem. But sometimes computing a Grobner basis is computationally intensive, sometimes it's infeasible, and moreover, sometimes it's useless, in the sense that it is possible to solve some problems without the use of Grobner basis. This leads to degrobnerization. So observe again your problems. Okay, if you have got a Grobner basis, okay, maybe you have got your solution, but maybe there are also other ways in order to get the same solution, for example, using combinatorics, using linear algebra, and you can restrict the use of Grobner basis only when it is really useful, because Grobner bases are a powerful tool and it's better to use them when it's really needed. So this is my take-home message. When you study a problem, you can think about that. Maybe there is also another way. But let's start with one of the two approaches that I already mentioned: involutive divisions, involutive bases. Well, involutive bases rely on the concept of involutive division. What is this involutive division? Well, it's a preprocessing of monomials. It's a divisibility relation. By means of this divisibility relation, you will be able to associate to every leading term of your generating set some variables and to distinguish whether they are multiplicative or non-multiplicative. So for each leading term, you will have its multiplicative variable and non-multiplicative variables. When you have to make reduction, if a monomial is multiple of the leading term of some generators, you will choose the one such that it is a divisor only by means of multiplicative variables. So you have this thing that is multiple of this, and you have to multiply this one only by multiplicative variables. In this way, you have only one way in order to reduce, because for the same monomial, you may the same monomial may be multiple of many generators, but you choose one. You have only one way. Here there are two divisions that are actually famous. They are called Gianni division and Pomare division, with the rules in order to understand which are the multiplicative and non-multiplicative variables. And in particular, if you are interested in, you can check the definition with the example here, in which there is a small set of terms and the difference between the two divisions on what are the multiplicative and non-multiplicative variables. Let's move to the basis. The idea is that you multiply each polynomial by a non-multiplicative variable for its leading term, and you make the same kind of reduction, but you use only the involutive divisor. This involutive divisor is exactly that monomial that I indicate with a circle, such that to get your monomial, you only have to multiply by multiplicative variables. So in this way, you make better reduction. You have only one way, but you get in any case also the S polynomials that you had. So you get the same S polynomial, you do that step by step and with a better reduction. Why do I say I get the S polynomials and I do it step by step? Let us consider this generating set. The leading terms are those x3, y3, that form my set U. And actually at this J, I took Gianni division. And the multiplicative variable for the first leading term is X, so Y is not multiplicative. And Y3 has got both of them to be multiplicative. What do I say? Okay, multiply each polynomial with a non-multiplicative variable. So I take this one and I multiply it by Y, that is non-multiplicative. I get this thing here. This polynomial is still irreducible. Then I continue, I multiply again by this non-multiplicative variable, and I get again a polynomial that is irreducible. So I multiply one time again, and I get this polynomial here. This polynomial is reducible with respect to F2. Indeed, you have x3, y3. So in order to get to x3, y3, you should multiply y3 by a power of x, and x is multiplicative for y3. So, okay, I multiply with y3, with x3, and I can make this reduction. Well, the first reduction step gives exactly you the S polynomial between F1 and F2. This kind of bases, are mainly used in applications in physics, but there is also some study that is nearer to crypto. In particular, the most famous division, Pomare division and Gianni division, have been also used to study involutive bases over Boolean rings. So you are over F2, F2, X1, Xn, modulo the field equations. In this case, you have variables that have only exponents 0 and 1. So it's good for memorizing them with vectorization. There is a problem that is with term orderings. Indeed, this is a problem for Gianni division and also for Grobner basis. Actually, for the classical Grobner basis, this is a problem as well, because you lose term ordering. Now I will show what I mean. Multiplicative is a problem in the sense that every time you have exponents that are 0 and 1. So suppose that this holds. Xy is smaller than z for your term ordering, okay? Well, multiplicativity says that if I multiply both sides for the same monomial, I should get the same inequality. Okay, let's multiply by xyz and xyz again. Well, since I'm here, the exponents are 0 and 1, so for both sides, I get xyz. So xyz is equal to xyz. And the inequality is not preserved. It is possible to prove, and it has been proved in a paper specifically for Pomare basis, that this problem doesn't occur when, well, you can compute in any case Boolean involutive basis directly here using Pomare basis. For Gianni division, for example, instead, you have to compute here your basis and then make the image in the quotient. Let's move now to linear algebra. let's move to linear algebra. Well, this Macaulay matrix was born in the context of homogeneous polynomials and used to study the structure of primary areas. What is this Macaulay matrix? Well, I take a polynomial set of some degree di, and for each degree d, you have a matrix whose columns are indexed by the terms of degree d, and the rows by the polynomials of the form tfi, with the degree of t that is d minus di. What are the entries? The coefficient of the monomial in the column in the polynomial in the row. And you can extend the same thing also to the non-homogeneous case. Well, the difference is that you have to take terms of degree smaller than or equal to d, ordered with respect to some term ordering, and then the entries are again the coefficients. You can use this linear algebra approach and this Macaulay matrix for some algorithms that we will explain a little bit in the next slides. Let's start with F4. In F4, by Fourier, you can reduce all S polynomials all in once. In the rows of your matrix where you put the polynomial, there are also the two pieces that you subtract in order to make an S polynomial. Moreover, there is also a reduction on the redundancy on the generators that you use in order to reduce. The idea is you start from your set F. Then you remove some useless polynomial for theoretical reasons. So for example, those whose leading term is multiple of the leading term of some other element. So you already start with a smaller set. You also use criteria, Grabauer-Müller criteria for S polynomials, and you create a set that in the beginning has got the two pieces that you need for make useful S polynomials, and you add only the multiples of the generator that are really useful to reduce. From this set, you construct the Macaulay matrix, of course, using only the monomial that really appear, and you reduce. You make Gaussian reduction on the matrix, and this allows to reduce all the polynomial, all these S polynomials only once. If you get some non-zero row from this reduction, you check the leading term of the corresponding polynomial, and you say, well, if the leading term is not multiple of something that you already have, you put it in the basis. And this kind of algorithm terminates when everything goes to zero. For F5, the first note we have to say is that, well, we know that in Buchberger algorithm, when you have to reduce a monomial, you have too many choices. Involutive basis found the limitation on the number of choices by means of the division and the fact that you want to use the involutive divisor. F5 tries another way to do, and it uses signature. So we'll define signature. We'll see good and bad, let's say, about this method. In particular, you will see, a problem and a solution on this method. Let's start with your polynomial set and define this map from P to the power U to P. So we take these elements where these EI are the tuples with one in ith position and zero everywhere else, and define this map by substituting, let's say, this EI with the polynomial Fi. We call a labeled polynomial a pair of the form, well, F is actually a polynomial, and this Ti is an element of T of U, where of course we can define an ordering that is compatible with that of polynomials. The signature of this labeled polynomial is exactly this element. We call it admissible if it comes from an element of P of U. So if there is an element of P of U such that the image modulo the map is the polynomial and the signature is exactly the leading term of this element here, this H. So this pair, admissible and labeled, is called normalized if you say the leading term is not already multiple, it's not in the set. And if you consider R and S of this form, you can define this pair where you have V, this element, times the signature of S, and this SFG, Oh, here there is a prime that should not be a prime here. We call it normalized if UR and VS are normalized. Then you say that F is a Grobner basis of the ideal if and only if for each pairs of this kind, either S is 0 or there is an H in P of U with the leading term that is smaller than this least common multiple. The idea of the original algorithm is that, well, you have the basis until the polynomial, let's say fi plus 1, so fi plus 1 fn, and you want to add fi, of course, all in terms of these pairs. You take the normalized pair of some degree, and similarly to f4, you produce polynomials in order to make them a polymetric and make a reduction. In the reduction, you keep the signature maximal. What's the problem was that it related to proving determination of the algorithm. It was not possible to prove it because, well, when I define such polynomials, I can choose the minimal signature. In this way, I minimize the number of elements in P of U in order to represent as polynomials. But if I start from 2 elements of minimal signature with the reduction, I cannot grant minimality anymore. What's the idea to solve it? By Harry, Eder, and Perry, it is to reduce using signatures in increasing order. So you start with minimal signature, you check that the signature and the leading term that you get cannot be divisible by something that you already have, and only in this case you put them in basis. But let's move to something more cryptographic. Let's go to Hildenfield equation. It is a scheme. You can make an encryption scheme, a signature scheme. The basic version has been attacked, so you use it actually to make either signatures or schemes that are more complex. Let's take K field is an extension, and phi is the map that maps k to the power n, the isomorphism between k to the power n and e, while f is the map defined by this big polynomial, where I only want to remark that this d here is a parameter that allows efficient inversion of the map. So in this way, you get a quadratic map over k to the power n, and you can define t and s to affine maps. The secret key is given by s and t and by f. The public key instead is given by this composition, which is again a quadratic form, quadratic from k to the power n to itself. Well, for encryption, you take z in k to the power n, and what you do is evaluating this, the system in z. In order to decrypt, you have got the secret key, so you can invert s. Then you use phi on the result, and you compute this set, the set of all y's, such that f of y is equal to z. It will be done by Berlekamp algorithm that we will see in the next slide. Well, for each of these solutions that you have computed, you can use phi to the -1 to move to k to the power n, and these t-1 of these elements are the candidate plaintext. Since there are more than one solution, but you want to recover your message, you have to distinguish between them. And in particular, you may use hashes. There has been a direct attack by Fougère and Zhu to this Hildenfield equation that managed to work because when you compute a Grobner basis, you don't increase too much in degree. Let's see also a bit what is this Berlekamp algorithm. Well, it's an algorithm to solve a univariate equation of high degree, but you want it to be square-free, co-prime with the derivative, and so you want to factorize in the reducible factors. If it is not square-free, there is an easy algorithm to make it. That is actually, you check whether it is divisible by the derivative, and if it's so, you divide it. If the GCD is 0, instead, you know that f should be the p power of a polynomial, so you only have to extract the p's roots and do it again. So it's easy to have a square-free data. In order to perform this algorithm, you have to compute this matrix, Berlekamp matrix, in which you have this Qij, the entries of the matrix that are a coefficient of the monomial x to the power j in xiq modulo f. Well, what is the idea of the algorithm? You have to build your matrix and find the basis of the kernel of QF minus I. If in the basis there is only one element, it is irreducible. Otherwise, for each element in the basis from the second on, and for each S in FQ, you compute this GCD between f and x and vi of x minus s. That is, if it is not one, is an irreducible factor. And so you can divide it off P. Of f, actually, the polynomial was f. Another special algorithm is this XL algorithm that stands for extended linearization, that has been proposed by Courtois, Klimov, Patayan, and Shamir in order to solve multivariate nonlinear systems over finite. What is the general idea? We'll take your system, extend it with all the polynomials of the form HF. F is a polynomial, F is a polynomial, H is a term, up to some given degree D, and perform again Gaussian elimination, in which you consider each monomial actually as a variable. And if D is large enough, you will find a univariate polynomial that you can solve with Berlekamp. Then you can substitute the solution inside the system and repeat again. There are some variants that are called FXL, XL2, and mutant XL. FXL says, well, first fix the value of some variables and then you run XL. In this way, you have a smaller D. The problem is you may have to run these algorithms more than once, because if you make a wrong guess, you have to do it again. XL2 instead is using F2, and actually the difference is that in the elimination you use the field equations. In mutant XL, you have that sometimes you can find polynomial whose degree is less than expected, that are called mutants, and the idea is adding them to the system and privilege them in the extension phase of the system. Finally, last 3 slides, and I don't know whether I'm too long or not, but there are really 3 or 4 slides and I'm over. We will deal with quadratic systems. So from now on, the systems are quadratic. And in particular, first case, number of equations is more or less a square of the number of variables. In particular, this is the right proportion. In this case, you can use the relinearization method to solve the system in polynomial time. That is, well, take each quadratic monomial that will become a new variable. So as a new variable. In this way, you will get a linear system with this times n plus 3/2 variables. You can solve the system with Gaussian reduction. With high probability, you will have a unique solution that corresponds to the solution of the original quadratic system. But you can also have the opposite case, in which the number of variables is more or less the square of the number of equations, again with this kind of proportion. You can use this Hashimoto's method. So, well, the idea is, well, you decompose the system in the composition of these 3 maps, where S and T are linear maps. And from this one in the middle, you can get some linear equations. So there is a linear part. And if there is a solution, substituting into the system would lead to the value of a variable, in the sense that you can find a quadratic univariate equation, solve it, and find the value. When you have found the value, you can substitute it in the system and repeat until you find them all. And finally, systems such that the number of variables is this mu m, with mu bigger than or equal to 2, but strictly smaller than m, because if it was equal to m, you could revert to the method before. The main idea is that a multivariate quadratic system with m equation and this mu m variables can be solved in about the same time as a multivariate quadratic system of this number of equations and variables. So given the system, you find a linear map that transforms the system into this new form. A system of m equation and n variables with components of this form. This L stands for linear. This thing is quadratic, for example. So you will then invert f prime and t. Actually, you use pieces of the systems to find variables one at a time. And in this inversion part, f prime will be transformed into a new system that actually has this number of quadratic equations that can be solved, for example, with Grobner basis method. In order to conclude, this was quite fast, but if you are interested in, there are some readings that you can make divided by topic. So for example, if you want to read about Grobner basis or involutive basis and F4 and 5, the works I was talking about Pomaresian division, sorry, this should have been capital, and also a book on multivariate post-quantum cryptography. Okay, I'm over. I hope I have not been too long, and I thank you for your attention.